Hi, this is your video for section 6.2 about the binomial probability distribution. Now, binomial probability experiments are just a specific kind of probability experiment where we have discrete probabilities. So if we have an experiment, we call it a binomial experiment if it meets these requirements. First of all, the experiment has to have a fixed number of trials. So maybe we have 5 trials, or 10 trials, or 100 trials, but it's not an unlimited number of trials. The second requirement is that the trials have to be independent. That means that the outcome of any one individual trial doesn't affect the probabilities in the other trials. The third one is that each trial must have all outcomes classified into 2 categories, and we usually refer to these as success and failure. So it could be something like yes or a no, on or off, defective, not defective, but it has to have only 2 outcomes. So out of our 2 outcomes, success and failure, if we look at the probability of a success in each trial, it has to be the same for each trial. When we're talking about binomial experiments and binomial probability distributions, we have some specific notation. So n denotes the fixed number of trials. This is just like us using n for a sample size. X is going to be our random variable, and for a binomial experiment or probability distribution, the x is going to denote how many successes we had in our n trials. And what this means is that the possible values for x can be any whole number between 0 and the total number of trials we had. A small p is the probability of success in any one of the n trials. So since success and failure are complements of each other, if p is the probability of success, then 1 minus p is going to be the probability of failure. And finally, uppercase P of x gives us the probability of getting exactly x successes among the n trials. Now, some hints for binomial experiments and probability distributions. First of all, be sure that the x and the small p both refer to the same category, which we're calling a success. So if you decide which of the 2 outcomes you're going to call a success, then that needs to be what the x values stand for, is how many successes there were, so how many of that particular outcome there were in the n trials, and the small p needs to be the probability of that particular outcome. Now, the independent trials requirement technically means that we have to be sampling with replacement. But if the population is large enough in the first place, then sampling with or without replacement doesn't make a significant difference in the probabilities. So that requirement where the probabilities have to be the same for each trial, if we have a large population, then if we're sampling without replacement, it's still not going to make enough of a difference in the probabilities to matter. So when we're sampling without replacement, we still consider our events or our trials to be independent if our number of trials, the lowercase n, is less than 5% of our population size. Capital N is our population size. So if we have an experiment where we know we're sampling without replacement, then we have to test and see whether our number of trials is less than 0.05 times our population size. If it is, then we can still consider it as a binomial experiment because we still consider each trial to be independent. Alright, so let's just start by identifying some binomial experiments. So we're thinking about those requirements and seeing if all of them are met in some certain situations. So first of all, if a player rolls a die 7 times, On each roll, the number that comes up is recorded. So we want to see whether this qualifies as a binomial experiment or not. So looking at those requirements, we have a fixed number of trials because we already know that the player is going to roll the die 7 times. So our number of trials is 7. Now the trials are independent because each time the player is doing a separate roll. So there's nothing from, say, the first trial that's going to affect any of the later trials. So that requirement is met. Now because on each roll the number that comes up is recorded, that means on each roll there are 6 possible outcomes, the numbers 1 through 6. That means that we have more than 2 possible outcomes for each trial, and that means that this is not a binomial experiment. For binomial experiment, we can only have 2 possible outcomes for each trial. So this one doesn't qualify. Now this next experiment, if a player rolls a die 7 times and the number of 6s that comes up is recorded, this is the same setup to start with. We have 7 trials, the trials are independent, and now we have only 2 outcomes for each trial because all we're paying attention to is whether the die comes up as 6 or something else. So our 2 outcomes are either 6 or not 6. So we're meeting that requirement. And finally, the probability of success, if we define success as rolling a 6, is going to be the same for each trial. It's going to be on each roll of the die, the probability of getting a 6 is going to be 1/6. So this one does meet all the requirements and is a binomial experiment. If you notice, the difference between these two is that the first one we had more than 2 possible outcomes because we were just recording the number that came up on the die. That gave us 6 possible outcomes for each trial. On the second one, we were only recording whether it was a 6 or not, and that gave us 2 possible outcomes. Okay, here's another example. In a class of 30 students, 55% are female. The instructor randomly selects 4 students without replacement. The number X of females selected is recorded. So again, we're looking at those requirements. First of all, our number of trials would be 4 because the instructor is selecting 4 students. As I said before, the number of trials a lot of times is the same thing as a sample size. Now in this one, because we're selecting without replacement, we have to see whether we can still consider the trials to be independent or not. If we were selecting with replacement, we wouldn't have to worry about this, but selecting without replacement, we do. So we're going to use this test. We're going to see if the number of trials is less than 5% of our population. Our population size is 30 because this was a class of 30 students. The number of trials is 4. So the question is 4 less than 0.05 times 30? Well, 0.05 times 30 is 1.5, and 4 is not less than 1.5. So the answer is no. That means that we can't consider these trials to be independent, so this doesn't qualify as a binomial experiment. Now, if we wanted to fix this so that it would qualify as a binomial experiment, we'd have to select with replacement. One more example. This time we've got census data that shows that 55% of Denver residents are female. 10 residents are randomly selected without replacement. The number X of females selected is recorded. So we have somewhat the same setup as the last example, only we're selecting our sample out of Denver residents instead of out of a class of 30 people. So we've got a fixed number of trials. Again, this is the same in this case as our sample size. So our n is equal to 10. Again, we're selecting without replacement, so we have to do this test to see if we can still consider our trials to be independent. This time, because our population is Denver residents, we don't know the exact population size n, but we can make some assumptions here. if we have any idea what the population of Denver is, we know it's pretty large. Is it 500,000, 1 million? It's something pretty large. We can make that assumption. And our number of trials is only 10, so this would definitely be less than 5% of our population size. So we don't have an actual number that we can put in for the population size, but we can make an assumption, and with this small sample size, we would know that the sample size would be less than 0.05 times that population size. So here we could consider the trials to be independent, so that requirement is met. And since all we're doing is recording whether the residents selected are female or not, that means we have 2 outcomes for each trial, either female or not female. So it meets that requirement. And finally, the probability of success, if we assume a success is selecting a female, then the probability of success for each trial is 55%. So it's going to be the same for each trial, so we're meeting that requirement. So we met all the requirements, which means we do have a binomial experiment. And we've got several methods for finding binomial probabilities. We can use technology, we can use tables, and there is a formula for this also. What we're going to do in this class is use technology, either your TI 83 or 84 calculator or StatCrunch. Now, if you don't have access to your calculator or StatCrunch, if you're doing homework or a problem somewhere and you don't have access to that, you can use the tables for some problems. You'll find tables for the binomial probabilities in the back of your textbook, or if you are using your ebook, then there's an appendix with all kinds of tables in it, and the binomial probabilities table is one of those. Now, the third option is using the formula. You won't be required in this class to use the formula. You may run into some homework problems that mention using the formulas. If it says that, please feel free to use technology instead. Let's look at how to use your TI 83 or 84 calculator to get binomial probabilities. For this, the function that we're going to use is binom_pdf. To find this function, press second and the vars key to get to the distribution menu. The binom_pdf function is the 11th one in this list, so you'll have to scroll down to a second screen in order to find it. So once you've found it, highlight it and press enter. And be sure that you're getting binom_pdf and not binom_cdf, because they're 2 different things. So depending on how new your calculator is, you will either see the function name come up on your screen, or you'll get a screen that looks like this. In either case, you need to fill in the values for n, p, and x. If you just get the function coming up on your screen, it'll give you an opening parentheses, and then you put the values in this order. N first, and then a comma, and then p, and then another comma, and then x, and then a closing parentheses. Now if you get this screen, the number of trials is n, so here's your n, here's your p, and here's your x. So take a minute and try this with your calculator. Put in these 3 values, so 5 for n, 0.1 for p, and 3 for x, and make sure that you get this value, 0.0081. And this one is rounded to 4 decimal places. You'll probably get something that goes out to more decimal places on your actual calculator. Now once you've gone through this process once, you can get the function back on your screen by pressing second and your enter key. This is just a shortcut so that you don't have to go back to this distribution menu every time. Now once you have that function up on your screen again, you can just backspace and change the values in the parentheses to get a different probability. Now when we're dealing with discrete probabilities, which binomial probabilities are one specific type of discrete probabilities, it's very important how we translate the wording of problems into math symbols. So some phrases that you're going to run into are at least, no less than, or greater than or equal to. All three of these would translate into this symbol, a greater than or equal to. And the important thing here is which values are included and which values aren't included. Since we're talking about discrete probabilities, it makes a huge difference whether you include certain values or not. So this would mean that whatever value you have here is actually included in your list because of the equal sign being with that. Now if we have a more than or a greater than, that translates into just a greater than symbol, and that means that the actual value that's over here is not included because there's not an equal symbol here. Fewer than or less than translates into a less than, and again this means that whatever value is here is not included. No more than, at most, or less than or equal to translates into less than or equal to sign, which means we are including the value. And exactly, you'll see this one a lot in these problems, exactly or equals or is translates into an equals sign, and that means we're dealing with one value only. Here's some examples. According to the Experian Automotive, 35% of all car-owning households have 3 or more cars. So the first question is, in a random sample of 20 car-owning households, what is the probability that exactly 5 have 3 or more cars? Well, first we need to make sure of whether this is a binomial experiment or whether we're dealing with something different. So if we look at those requirements again, we have a fixed number of trials because we have a random sample of 20 households. So our number of trials is 20. Since the population of car-owning households is going to be extremely large, we can assume that our number of trials, 20, is going to be less than 5% of that population size. So we would consider the trials to be independent, even though we would be selecting without replacement. And we do have 2 possible outcomes, and that is either the household has 3 or more cars or it doesn't. And our probabilities are going to be the same for each trial because we have this information that 35% of all car-owning households have 3 or more cars. Our probability of success on each trial would be 35%. Okay, so the 2 outcomes for each trial are success, that there are 3 or more cars in the household; failure, there are not 3 or more cars in the household. And this is something that we can define when we're setting up the problem. So I just decided to define success as there being 3 or more cars in the household. And one way you can look at this is look at what question you're being asked. What are you trying to find the probability of? Up here, we're trying to find the probability that exactly 5 households have 3 or more cars, that they do have 3 or more cars. So that's one reason that we could define this event as something, as a household having 3 or more cars, as our success, because that's what we're trying to find a probability for. And again, since we already know that 35% of the households do have 3 or more cars, that means the probability of success on each trial is 35%, or we have to put this in a decimal form to use our calculator, so this would be 0.35. And the question that we're asking is the probability that exactly 5 have 3 or more cars. So we're looking for exactly 5 successes. This translates to just x is equal to 5. We're looking at just a single value here. So we want to find the probability that x equals 5, or we usually write this as just p of 5. On your calculator, you would put in 20 for the n, 0.35 for the p, and 5 for the x. And remember to make sure that this is binom PDF. And if you calculate this, you should get 0.1272 if you round it to 4 decimal places. So again, try this out on your calculator and make sure that you're getting this value. Let's look at another probability problem with the same experiment. So here we want to know the probability that at most 5 of our 20 households have 3 or more cars. At most 5 is going to translate to x is less than or equal to 5. So we're trying to find the probability that x is less than or equal to 5. And what this means, because we've got the equal sign here, is that we're going to include 5 in our list of outcomes for our event. So the outcomes we're including in this event are everything from 0 up to 5. Now going back to our probabilities from Chapter 5, since these events are mutually exclusive, we can't have both 1 and 2 households that own 3 or more cars. It has to be only one of these. So that means that we can use the addition rule for probabilities, which means we can add up, we can find the probability for each of these and then just add the results together to get our probability. So this would be one way to calculate this probability. This would mean you'd have to put in binom PDF and put in 0 for x. Here you'd put in 1 for x, 2, 3, 4, and 5. So you'd have to do that function 6 different times and then add all the results together. That's kind of a lot of work. So there is a shortcut. There's another function on your calculator that instead of binom PDF is binom CDF. The C stands for cumulative. So what this does is it finds the probability for x less than or equal to C for whatever value of C you put in here. So if we wanted to find the probability that x is less than or equal to 5, we would put a 5 in here in place of the C. Now this only works this direction, so as long as we have a less than or equal to, then this will give us the answer that we're looking for. So to use it here, you would get this function on your calculator, the binom CDF, put in 20 for n, 0.35 for p, and 5 for x. The value you get should be 0.2454, rounded to 4 decimal places. So test this out and make sure that you can get this value. Now another problem with this same setup. Now we want to look at the probability that at least one of the households has 3 or more cars. So first we need to translate this into symbols. At least one translates to x is greater than or equal to 1. So what we're looking for is the probability that x is greater than or equal to 1. In terms of outcomes, x greater than or equal to 1 would include all the possible values for x from 1 all the way up to 20. Remember for a binomial experiment that the possible values for x go all the way from 0 up to our number of trials, which is 20. Now the problem here is that our binom CDF function that we just looked at calculates less than or equal to. It does not calculate greater than or equal to. So that one isn't going to help us here. And we certainly don't want to put in one function for each of these 20 numbers and then add all those results together. That's way too much work. So a shortcut to do this would be to use the complement rule. So the complement of the event at least one success is no successes. So the complement of this event is just that x is equal to 0. So what we can do is we can find the probability that x is 0, or the probability of no successes, and then subtract that probability from 1 to find the probability that we're actually looking for. So since we want the probability that x is actually equal to 0, we would use our binom PDF function, which just calculates one value, put in 20 for n, 0.35 for p, and 0 for x. This would give us 0.00018. If we round this to 4 decimal places, we get 0.0002. Now that's the probability for no successes. to find the probability for at least one success, we have to subtract this from 1. So if we do 1 minus 0.0002, we get 0.9998. So the probability we're looking for of at least one success is 0.9998. Now let's look at a different problem. In this one, a player rolls a die 7 times. The number x of 6s rolled is recorded. Construct a probability distribution table for this experiment. Now this is the same problem that we looked at when we were identifying binomial experiments, and we already determined that this one met all the requirements for a binomial experiment. In this one, we only have 2 possible outcomes for each trial. Either it's a 6 or not a 6. So our random variable x represents the number of 6s rolled out of the 7 rolls of the die. That means our possible values for x are anything from 0 up to 7. So 0 would be if we got no 6s in our 7 rolls. A 3 would be if we got 3 6s out of the 7 rolls. 7 would be if we got a 6 on every roll. So for our probability distribution, we've got x, and in this column we have all the possible values for x, so from 0 up to 7. Now to fill in the other column, we have to find the probabilities for each of those values. So for each value of x, the probability of x is the probability of exactly that many successes. So what we can do is use the binomial PDF function to calculate each probability value. So our number of trials, n, is 7, and the probability of success, rolling a 6 on each trial, is 1/6, which you can put this into your binomial PDF function, just like this, 1 divided by 6, or you can round it to 4 decimal places and get 0.1667. So here's how we would calculate the probability for 0 successes. We put in 7 for n, 0.1667 or 1/6 for p, and 0 for x. And in this case that comes out to be 0.2790, rounded to 4 decimal places. The probability for exactly one success is 0.3907. We would do this for each different value of x, and again all you would have to change here is the x value, and do this for each one of these different values, and you would get all these probabilities. Now when you get down to the probability for 7 successes, you actually end up with a very small number. And if you do this on your calculator, you'll probably see something like this, 3.577, and then an E, a capital E, and a -6. What this is doing is putting this in scientific notation. So this is like 3.577 times 10 to the -6. What that means is that you have to move your decimal point 6 places to the left. So this would be the same as 0.000003577. So here are all the values you should get for your probability distribution. And in this one, if we rounded it to 4 decimal places, we'd actually get 0. I went ahead and put in all the decimal places just so that we could see what it was. And again, if you've done this correctly, if you add up these values, you should get 1. Now it's possible sometimes to get a little bit of rounding error, so this might actually turn out to be something like 0.99 or 1.01. That's okay as long as it's rounding error. If it's any farther away from 1 then you ought to go back and check to make sure you haven't made a calculation mistake somewhere. Now these are some of the easiest formulas in this whole class. This is the only time where I'll actually have you calculate a standard deviation because the formula is so easy. So for the mean for a binomial random variable, it's just n times p, again, where n is the number of trials and p is the probability of success on any one of the n trials. So the mean is n times p. The mean, since we're talking about a discrete probability distribution, the mean is the same as the expected value. So this is the mean, it's also the expected value. For the standard deviation, you take the square root of n times p times 1 minus p. Let's go back to our example dealing with car-owning households. If we have a simple random sample of 400 car-owning households, determine the mean and standard deviation for the number of car-owning households that will have 3 or more cars. So in this one, we do have a binomial experiment. In this one, our sample size is the same as our number of trials. So our n is equal to 400. And again, we're going to define success as the household having 3 or more cars. Our probability of success on any one trial is 0.35. So we can calculate the mean or the expected value for this distribution. It's just n times p, or 400 times 0.35, and that gives us 140. This is the same as the expected value, so in any group of 400 households, we would expect that about 140 of them would own 3 or more cars. Now that's a little bit misleading because if we picked out several different samples of 400 households, that doesn't mean that necessarily any of them would have exactly 140 successes. Remember that expected value really is talking about the long run. So what this would, so a little bit more accurate interpretation of this would be if we selected a large number of simple random samples of 400 households. Say if we selected 1,000 different samples of 400 households and looked at the number of successes in each one of those 1,000 samples, the average number of successes we would expect to be 140. So that's really what this is talking about. Our standard deviation, again, this is an easy formula. All we have to do is take the square root of n times p times 1 minus p, and that gives us 9.5. So if we're thinking about mean and standard deviation, we've got a mean of 140 and a standard deviation of 9.5. Now let's look a little bit more at binomial distributions and the mean and standard deviation. If we look at probability histograms for binomial distributions, we can see that the shape of the distribution depends on the number of trials n and the value of p. So in this picture we have a binomial distribution where we have 30 trials. Our probability of success p is 0.35. So you can see in this picture that the distribution is skewed to the right a little bit because there's a longer tail on the right side and more of the data is actually on the left. So our mean for this distribution is 10.5, and that again is not exactly in the middle between 0 and 30, but it's a little bit to the left of the center. And our standard deviation is 2.61. Now if we have the same number of trials, so if we have 30 trials, but our probability of success is 0.5, then we have a symmetric distribution. Notice that the mean for this distribution is 15, which is exactly halfway between 0 and 30. So this distribution shape is symmetric and it has somewhat of a bell shape. Our mean is 15 and our standard deviation here is 2.74. Now finally, if we change our probability of success to 0.9, look what it does to our distribution picture. In this picture, our distribution is very much skewed to the left. Notice that there's a tail out on the left side, and most of our data is centered here on the right. Our mean for this distribution is 27, so it's clear over here on the right end. And our standard deviation is 1.64, because actually in this case, the bulk of our data is closer together and is closer to the mean than it was in either of these two pictures. So our standard deviation is a little bit smaller. Now, what if instead of changing the value of p, we change the value of n? Let's look at three pictures with different n values. So here we've got a probability of success of 0.35, and our sample size, or our number of trials, is only 5. So our possible values of x only go between 0 and 5. And notice what our distribution looks like. Again, we can see that it's skewed a little bit to the right because we have a longer tail over here. Our mean is 1.75, so it's pretty close to the 2, which has the highest probability value, and our standard deviation is 1.07. In this picture, we still have p equal to 0.35, but our number of trials is 30. So notice how this distribution is more spread out because our possible values of x go from 0 to 30. Our mean here is 10.5, which again is a little bit to the left of our middle point between 0 and 30. And our standard deviation is 2.61. So actually this distribution has a little bit more variation than this one did if we're just comparing standard deviations. Now finally, let's look at the same probability of success with 100 trials. Now this one has even more of a bell-shaped type distribution. Although this is still going to be skewed to the right because our p-value is 0.35. But you can see as we increase the number of trials that this is starting to look more and more like a bell-shaped distribution. And remember, when we're calculating this mean, the mean for a binomial distribution is just n times p. So as we increase our number of trials, then our mean is going to increase. So it went here from 1.75, which is a little bit to the left of the middle of this graph. Here it's 10.5, which is again is a little bit to the left of the center of the graph. And here it's 35, which is also a little bit to the left of the center of this graph, which would be 50.